Slug flow is a multi-phase flow regime where gas coalesces to form large bubbles. These bubbles are in the form of bullets and are known as Taylor bubbles. The liquid alternating between the Taylor bubbles are commonly known as slugs. This alternation of liquid and gas creates pressure oscillations which can lead to separator flooding and hydraulic hammering. These problems become more pronounced in offshore risers. Our objective is to better understand the slug flow phenomenon and mitigate its negative effects. Our team has and constructed two different size models, the smaller being the bench scale model and the larger being the pilot scale model. We will also use computational fluid dynamics to provide validation and hopefully better control methods. We created our geometry with Fusion 360, mesh was done with ISOM, and the simulation is done with ANSYS Fluent. Now we will discuss briefly the concept of PID control. PID stands for Proportional Integral Derivative. A PID controller looks at the error between the user-defined set point and the process variable. The controller then implements the proportional control to return the process variable to the set point. Although using the proportional alone will leave a steady-state error, the integral part tries to reduce this steady-state error. The last portion is the derivative, which tries to reduce overshooting and usually acts against the proportional and integral portion.
The first step in simulations was the construction of a geometry of the physical model. We used Fusion 360 to make a simpler version of the model, and because we're only concerned about the flow physics in the riser, the geometry does not need to include the pumps and sensors. Later we simply input the different injection velocities as boundary conditions and declared the edges of the pipe as no flow boundaries. Next, the model was meshed using ANSYS ISOM. For the first few simulation runs, we chose to use a coarser mesh to lessen the computation time needed, and then refine the mesh and run again to compare the differences. Here you can see the coarse mesh of the bench model, which consists of 180,000 nodes. The refined version contains over 400,000 nodes. Once this step was completed, the mesh files were read into a case file for running the simulation in ANSYS Fluent. Daniel and Mark attended training at the LSU High Performance Computing Center to learn about the capability of LSU resources and become familiar with the Linux-based user environment needed to interface with a supercomputer. The first few simulations were run on a single node within the SuperMike platform and took about 10 hours to calculate 20 seconds of flow time. We used the time discretization of 0.001 seconds and recorded the data every tenth of a second. Here's a graphic of the phase contours at 14 seconds, which showed us we need to partition the riser before simulating if we want to later create animations with the view inside. This graphic shows the volume fraction of air inside the system with the mesh overlaid. After the first simulation, this contour showed us that the model accurately illustrates the occurrence of slug flow. We're in the process of creating GIF animations to see this in action.
You are looking at the bench model's control valve. It was implemented for future PID usage. The control valve is comprised of a 1.5-inch Schedule 40 gate valve with plunger and a 100mm linear actuator with feedback. The feedback allows our computer to see what position the valve is in. In order to power and control this valve, we had to add a voltage supplier as well as a L298N H-bridge to our Arduino Mega microcontroller. Through trial and error and a lot of long hours, we successfully have our computer controlling our valve autonomously. To set system parameters and retrieve data more efficiently, the team designed and implemented a graphical user interface with MATLAB. This allows the user a more friendly environment to read pressures and flow rates, adjust PID settings, and initiate emergency pressure purging procedures, and visually see the PID attempting to reach set point on the included graph.
The pilot model is basically a large-scale model of the bench model. The frame for the model is 25 feet long and roughly 20 inches wide, with a 5-foot outrigger on each side. The frame is constructed of 2-inch by 2-inch by 1/4-inch angle iron so that there will be a low center of gravity preventing the model from tipping. The main riser support is constructed of a 28-foot extension ladder that was welded together in the center for structural support. The riser portion is constructed of 2-inch Schedule 80 PVC pipe with 1.5-inch Schedule 40 PVC pipe as a return line. The water is pumped with a 15-gallon per minute centrifugal pump. The air is injected through a 40 to 400 SCFH flow meter. There are 3 0 to 200 PSIG pressure transducers that are mounted along the side of the riser to allow for pressure readings at different points in the riser. Similar to the bench model, there is an actuator control valve at the top. The entire model is powered from a 120-volt AC system that is reduced for the control module and transducers to 20 volts DC through an AC-DC converter. The constant airflow is supplied by a 1 horsepower, 15-gallon tank air compressor.